Hello everybody and a very warm welcome. My name is Joachim Weiss, and in this presentation I will guide you through the basics of ion chromatography. The next slide shows you the outline of my presentation. After giving you a short introduction with the definition of ion chromatography and the positioning of this method in comparison to other competing methods, I will briefly talk about the basics of anion and cation exchange chromatography with emphasis on stationary phases. Afterwards, I will briefly review the most important detection methods used in ion chromatography today. Let us start with a small introduction to the field of ion chromatography. Let me start with the definition of the term ion chromatography. In the early days of IC, the perception of the users was that this analytical technique is only good for the analysis of inorganic anions and cations. As you might imagine, this has changed dramatically over the years, so that ion chromatography today is an umbrella term for all liquid chromatography techniques that are suitable to separate and detect ionic and ionizable species. Ion chromatography was introduced in 1975 with a legendary article by Small and co-workers, who at that time worked at the Dow Chemical Company in Michigan in the United States. In their introductory paper, they described for the first time an ion exchange chromatography method with suppressed conductivity detection. This slide shows the schematic configuration of an ion chromatography system, which is not really different from any other traditional liquid chromatography system setup. We need a high-pressure pump with metal-free fluidics to transport the mobile phase through the system, and we are injecting the sample volume through an injection loop which is mounted on the injection valve. However, separation and detection are fundamentally different from traditional reversed phase chromatography. We all know that ions are not really retained on a reversed phase column. That means we need an ion exchange separator column for the separation of ionic species. Also, organic solvent-water mixtures cannot be used as a mobile phase. Instead, we need an electrolyte solution. Since most of the inorganic ions do not have any chromophores, traditional UV detection used in reversed phase chromatography can also not be applied. However, all the ions have one property in common: they are conductive, and that means conductivity detection up to the present day is one of the most fundamental detection systems in ion chromatography. As early as 1975, Hamish Small already mentioned the term suppressor device, which is nothing else but another ion exchange device positioned between the column and the detector cell to convert the mobile phase into a less conductive form, and at the same time enhancing analyte conductivity. Although ion chromatography is the most dominant method in ion analysis today, there are of course a number of competing methods on the market. Whenever the total metal content of a sample is of interest, people are usually choosing ICP in the two application forms, such as ICP-OES, optical emission spectrometry, or ICP-MS. However, if the oxidation state of a metal is of interest, then we have no alternative but to hyphenate an element-specific detection system such as ICP with chromatography to separate the two oxidation states of a metal such as iron 2, iron 3, chromium 3, chromium 6, and the various inorganic and organic forms of arsenic. Atomic absorption, also used up to the present day, especially graphite furnace atomic absorption, for the ultra trace analysis of metals, as well as a hydride generation system for the determination of antimony, arsenic, selenium, or tellurium. Polarography as an electrochemical method, still quite popular, especially for the ultra-trace analysis of selected metals down to the nanogram per kilogram level. Although polarography is not really a multi-component technique, usually more than one metal can be analyzed simultaneously. Titration, we all know, especially used today for determining ions at very high concentration, for example at percent levels, and ion selective electrodes. However, some of them are prone to interferences. I give you just an example. If we take a fluoride selective electrode and our sample contains large amounts of bromide, then we have to observe interferences with such an electrode. The list can be continued with capillary electrophoresis. Some 15 years ago, there was a lot of hype about this particular analytical technique because the speed of analysis was so much higher as compared to normal ion chromatography. The stationary phases in form of few thicker capillaries were very inexpensive, and the whole system setup on first view seemed to be very simple. However, flow rate accuracy and precision in chromatographic systems are much higher in comparison to CE, and this is due to the relative instability of the electroendo-osmotic flow. There's another fundamental problem with CE for small molecular weight ion analysis, and this is a lack of the most dominant detection system, and that is suppressed conductivity, which is still not available even with the most modern CE systems today. Also, when it comes to trace analysis, we see a number of problems with electrostacking techniques in CE. Whenever we have to analyze a large number of samples, and large means here definitely more than 50 samples a day, then chromatography is usually too slow. In this particular situation, we always use either flow injection analysis or segmented flow analysis, which is a perfect choice for high throughput analysis. We also see this kind of analysis today with a very high degree of automation whenever we are using auto-analyzer systems. However, the system might be a little more complex if many analytes have to be analyzed simultaneously, and we should also not forget that flow injection analysis or segmented flow analysis is nothing else but automated wet chemistry with exactly the same problems which we have observed in wet chemistry more than 40 years ago, before the introduction of ion chromatography. Last but not least, photometry, still very popular today, for instance for the analysis of nitrite or orthophosphate at very low concentration, an analysis which is usually done in contract laboratories photometrically. Let us continue with some fundamentals of anion exchange chromatography. The following slide schematically depicts the anion exchange process. Let us assume we have a resin particle to which quaternary ammonium functional groups are attached in one way or the other. We see these groups typically in the hydroxide form because the mobile phase contains a lot of water. If we have chloride ions in solution as an example, these chloride ions have a higher affinity to the stationary phase than hydroxide ions. That means they will shortly be bound on the quaternary ammonium group, releasing hydroxide ions, so that we can formulate the equilibrium on the bottom of this slide, which is governed by the selectivity coefficient capital K. On the right side, we see the formation of sodium hydroxide in this particular case. So if we want to push this equilibrium to the other side, to the left side, we just need to increase the concentration of hydroxide, and that means, in other words, that hydroxide may act as a mobile phase for transporting ions through an anion exchanger. The reason why we are able to separate chloride, as an example, from other halide ions is that can only be done if the selectivity coefficient capital K is different for these two ions under investigation. This slide shows the definition of the selectivity coefficient, and as we see from the formula, K depends on the eluent and analyte ion concentrations in the mobile or at the stationary phase. We also see that the selectivity coefficient helps us to estimate the effectiveness of an ion as an eluent in anion exchange chromatography. The next subject deals with retention determining parameters. Charge, size, and polarizability of an ion are properties that we cannot change as the operator of an ion chromatography system. Regarding the charge of an ion, we have a rule in ion exchange chromatography saying the higher the valency of an analyte ion, the larger its retention time. As an example, we typically observe the monovalent nitrate ion eluting ahead of the divalent sulfate ion, although we can design chromatographic conditions such as very high eluent concentrations where this elution order is reversed. The exception of this rule is retention of multivalent ions such as orthophosphate. We all know that the charge of orthophosphate depends on eluent pH, and therefore with different kind of eluent pHs in the mobile phase, we see different retention times for orthophosphate. There's no exception to the rule regarding the size of an ion. The rule says the larger the radius of the analyte ion, the larger its retention time. A perfect example for this rule is a series of halide ions. We always observe the small fluoride eluting first, followed by the elution of the other three halide ions such as chloride, bromide, and iodide. However, the retention difference between all these pairs of ions is increasing, especially the retention difference between bromide and iodide, and this has something to do with the term polarizability, which we will see on the next slide, saying that large ions such as iodide are undergoing non-specific interactions with the stationary phase, such as adsorption effects, and those adsorption effects are leading to a much longer retention time of large ions. The third term we have to discuss is the polarizability of an ion. Again, the rule says that the higher the polarizability of the analyte ion, the larger its retention time. In the example I've given here, we observe typically a much shorter elution of the divalent sulfate in comparison with a monovalent thiocyanate, and this reverse elution order can only be explained in the way that the ion exchange process is superimposed by adsorption processes. The most important part of an ion chromatography system is the stationary phase. There are numerous anion exchange materials on the world market, so that we have to classify all these materials. The number one classification is a type of the substrate material, where we differentiate between silica-based materials and organic polymers. Since we need high pH mobile phases in anion exchange chromatography, silica-based materials cannot be used because silica-based materials dissolve above pH 8.5. Therefore, most of the materials we are using for the anion exchange chromatography of small molecular weight anions are based on organic polymers. Regarding the pore size of the substrate materials, we differentiate between micro and macroporous ones, and this is related to the ion exchange capacity. That means microporous materials are usually of a low ion exchange capacity, whereas macroporous substrate are related to high capacity materials. This slide shows the most important organic polymers used in the design of anion exchangers today. In the early days, most of the columns were based on polystyrene codivinyl benzene. Today, the majority of columns are based on a similar material, which is polyethylvinyl benzene, codivinyl benzene. But in addition, we see polymethacrylate and polyvinyl alcohol resins. Polymethacrylates are usually used especially for the separation of sulfite and sulfate, or in a more general way for sulfur speciation, whereas polyvinyl alcohol resins show a very high resolution for inorganic anions. However, they are not as pH stable as the styrene-based materials. This slide summarizes the three major types of anion exchangers used today. On the upper left, we see the schematic of a nanobead agglomerated material, which was originally developed by Hamish Small at the Dow Chemical Company. This type of material is based on a substrate particle of a certain diameter, which is surface sulfonated so that we have negative charges on the surface, so that we can electrostatically agglomerate a series of nanobeads, and those nanobeads with a very, very small particle diameter of about 0.1 nanometer, those particles are carrying the ion exchange functional groups in form of quaternary ammonium groups. This kind of setup has one major advantage. The particle diameter is relatively large. However, the ion exchange reaction takes place at the nanobeads. That means the diffusion pathway is very short, the diffusion time very short, and we see a very high chromatographic resolution despite the larger particle size of the substrate. Those materials are still used up to the present day, especially for the separation of carbohydrates and oligonucleotides. There are some disadvantages with this type of resin as well. We see a lot of coelution problems in the early days of ion chromatography, so people developed grafted surface aminated resins, and those you see here on the right side as a schematic. We use the same type of substrate particle, but now not surface sulfonated. We are polymerizing 1, 2, or even 3 different monomers onto the surface so that we get polymer chains of about 5 nanometer lengths, and these polymer chains are carrying the ion exchange functional group. A major disadvantage of this type of resin is that now the chromatographic efficiency very much depends on the particle diameter of the substrate. On the bottom left, you see the most modern type of anion exchanger, which we call today hyper-branched anion exchangers. We do a very similar thing as with grafted surface aminated resins. That means we are grafting monomers onto the surface, but as a difference, those polymer chains are branching out, and all these branches are now containing or carrying the ion exchange functional groups, so that the analyte ion diffusing to the surface of the stationary phase are not reaching the stationary phase surface itself, where they can do some non-specific unwanted interaction. In other words, these modern hyper-branched anion exchange columns are the ones with the highest chromatographic resolution today. A much better way to understand the differences between the three different types of anion exchangers is to look to the chromatographic results. In the center, we see the chromatogram of a typical nanobead agglomerated stationary phase, such as the IonPEC AS4A, a column that has been developed many years ago. But even if we look to this kind of chromatogram today, many people are still liking this for a number of reasons. First of all 7 anions are separated to baseline within a relatively short time of less than 10 minutes. And also we see very symmetric peak shapes for all kinds of peaks. However, the fluoride is eluting in the column void volume and therefore cannot be quantitated very precisely. And also, if we would inject some disinfection byproduct anions such as bromate, chlorite, or chlorate, we would face a lot of coelution problems. Most of these problems, as you can see on the upper left, have been overcome with the development of surface grafted aminated resin, and a typical representative is the IonPEC AS14. However, we see that for this kind of separation we need a much longer time, resulting in higher resolution between the peaks, and very important, fluoride is well separated from the system void and can even be separated from small fatty acids such as acetic acid. But if we look a little bit more careful, we see a lot of rounding on the peak base for most of these peaks, and this has something to do with the ion exchange functional groups not only being at the surface of the stationary phase, but also in layers underneath. As we see on the lower right side, the IonPEC AS22 is the most modern stationary phase, carbonate selective, and as we see from this type of chromatogram, the selectivity is not changed. We see the same elution order, the same separation of fluoride from the system void, the separation of fluoride from acetic acid. Every other peak is baseline resolved, but the major difference to the IonPEC AS14 is that the peak efficiency for all peaks is much higher, so that we get a much better resolution with this type of hyperbranched condensation polymer. This slide shows the only two commercially available polyvinyl alcohol columns on the market, the Metrosep Sub 5 and Sub 7. Although these columns are 100% solvent compatible, their ion exchange capacity is relatively small and the pH range is not as large as with styrene-based materials. The separation of the 7 most important inorganic anions on such a polyvinyl alcohol resin is shown on this slide. I think we all agree the resolution between all components is exceptional. The only problem is the relatively long analysis time of more than 20 minutes, which cannot be decreased by increasing the flow rate. The standard flow rate, as we see, is 0.7 mils a minute, and this is due to the fact that polyvinyl alcohol resins are mechanically not as stable as their styrene-based analogs. A very important parameter in the discussion of ion exchange stationary phase is the ion exchange capacity of those resins. As mentioned earlier, we are differentiating between low capacity micropores and high capacity macroporous resins. A macroporous resin particle is shown on the right side of this slide. It has a pore size of almost 2000 angstrom, and that means that the nanobeads can diffuse into the interior parts of the pore. In this way, we can increase the ion exchange capacity of the resin by almost a factor of 10 without changing the surface area or the particle diameter of such a particle. Now, why are high capacity ion exchangers so important? And I just want to mention two reasons. First of all, the separation of equally charged ions with large concentration differences. A typical example is the separation of large amounts of chloride from small amounts of nitrite, and we know that these ions are eluting very close to each other. And such a separation problem can only be handled by applying high capacity anion exchanger. The second reason is the possibility to inject large sample volumes to facilitate trace level analysis. And when I say large sample volumes, I mean volumes all the way up to 1 or even 2,000 microliters. This allows us to analyze anions down to the microgram per liter or even sub-microgram per liter level. And again, this can only be done by applying high-capacity anion exchangers. Let us talk for a moment about eluents in anion exchange chromatography, especially when we utilize suppressed conductivity detection, the most dominant detection system in ion chromatography. In general, a lot of compounds can be used as an eluent when they are in aqueous solution anionic at pH above 8 or neutral between pH 5 and pH 8. Typically, we use salts of weak acids such as sodium hydroxide, sodium bicarbonate, sodium carbonate, or mixtures of them. As you see, the elution strength increases from sodium hydroxide all the way to sodium carbonate. If we are using suppressed conductivity detection, the suppressor product for sodium hydroxide is water, which has of course the lowest theoretical background conductivity. Whenever using carbonate-based eluents, our suppressor product is carbonic acid, and carbonic acid chemically is carbon dioxide dissolved in water. For more than 25 years since the introduction of ion chromatography in 1975, anion exchange chromatography was typically carried out using carbonate bicarbonate mobile phases. This slide lists the four major advantages of such an eluent system. For instance, the selectivity is determined by the concentration ratio, and that means the retention of mono and divalent analyte ions depends on the concentration ratio between carbonate and bicarbonate. It also means that we can elute mono and divalent analyte ions in the same run, and this even includes orthophosphate. The typical eluent pH of such a carbonate bicarbonate eluent system is 10.2. At this pH, orthophosphate is existing as a divalent anion, and this means we can elute orthophosphate together with other divalent analyte anions in the same run. Whenever we are preparing a carbonate bicarbonate eluent, typically using eluent concentrates that are even commercially available, we automatically have a very precise adjustment of the eluent pH. I can even calculate the eluent pH with the Henderson-Hasselbalch equation if I know the two pK values of carbonic acid. And last but not least, carbonate bicarbonate eluent systems represent a chemical buffer system. And this is very advantageous because in most of the cases my sample pH differs from the eluent pH. If I have a chemical buffer system, I can inject these kind of samples without extensive sample preparation. The only real disadvantage of a carbonate bicarbonate eluent is we can only use this under isocratic conditions. Those eluents are not suitable for gradient dilution for one major reason. The product of suppression is carbonic acid, which has a slight dissociation into bicarbonate. And this means if we are using a concentration gradient, we will generate more and more bicarbonate, leading to a very significant baseline shift during the gradient run. Already in the early 1970s, Hamish-Small already recognized that hydroxide would be a much better eluent for anion exchange chromatography, as a product of suppression is water with its very low theoretical background conductivity. However, the problem he could not solve at that time is the carbonate impurity in manually prepared hydroxide eluents. Whenever we do this on this planet with carbon dioxide in the air, this carbon dioxide will diffuse into the hydroxide solution where it is converted to divalent carbonate ions. In other words, our hydroxide solution would contain an impurity with a higher eluting strength than the mobile phase itself. This would lead to very inconsistent data, especially inconsistent retention times. The technological breakthrough came at the end of the 1990s with the introduction of reagent-free ion chromatography as it is called today. This slide shows the schematic setup of such a system, which is not much different from a traditional ion chromatography setup. The only difference is an additional module called the eluent generator, in which hydroxide or even carbonate bicarbonate mobile phases are prepared and generated in situ by means of electrolysis. The heart of an eluent generator is the so-called elugen cartridge. In this slide we see the schematic representation of the potassium hydroxide cartridge used for anion analysis. It consists of a reservoir in which we have a high concentration of a potassium electrolyte. This reservoir is connected via a stack of cation exchange membranes with a chamber in which the electrolysis takes place. This electrolysis chamber also houses one of the two electrodes, here in this case a cathode, while the other electrode is placed inside the electrolyte reservoir. If we are now pumping ultra-pure deionized water into this electrolysis chamber and apply an electric field between the two electrodes, the potassium ions start migrating under the influence of such electric field through the cation exchange membranes into the electrolysis chamber, where they pick up hydroxide ions generated at the cathode. Our final product is potassium hydroxide. But this is not the only reaction product. As you can see, we also generate a little bit of hydrogen gas, which has to be stripped before getting into the injection valve and finally be directed to the separator column. This gas removal is done with a very simple high-pressure degassing device. Since the whole reaction occurs under high pressure, namely the back pressure of the analytical column, we can easily imagine small amounts of impurities from the deionized water or ions at trace level leached out from the cation exchange membranes under high pressure. All these impurity anions can be removed with a continuously regenerated trap column positioned between the elugen cartridge and the injection valve. In the upper right, you see that the generated hydroxide solution or hydroxide concentration depends very much on the applied current. The higher the current, the higher the potassium hydroxide concentration. This potassium hydroxide concentration is also inversely proportional to the applied flow rate, which of course is always constant in a normal ion chromatography system. Now I can imagine two different scenarios. I can keep the applied current constant at all time. That means I would generate a constant hydroxide solution, and that means we are doing isocratic analysis. On the other hand, I can also imagine to program the current over time. That means I'm changing the hydroxide concentration over time, and this is what we typically do in a potassium hydroxide concentration gradient. This slide compares standard anion analysis under isocratic or under gradient elution conditions. The top chromatogram represents isocratic analysis using roughly 15 millimole per liter potassium hydroxide as a mobile phase. As we can see from this chromatogram, the first four components are easily separated to baseline, but then we have to wait a significant amount of time for the much more strongly retained orthophosphate. We also see the typical band broadening effect under isocratic conditions. When we compare to gradient elution conditions in the bottom chromatogram, we see two major advantages with this approach. First, we are achieving a much higher peak capacity. In other words, in a given amount of time, we can simply separate more components to baseline. The other effect is the higher sensitivity of later eluting peaks. As you can see, the peak shape of peak number 5, orthophosphate, is almost as good as the peak shape of the early eluting fluoride. That means we see higher peaks and higher sensitivity under gradient conditions. However, we also have to add the time for the re-equilibration of the column going back to the starting chromatographic conditions. This time, of course, has to be added when we compare cycle time for both approaches. However, we see here in this case that the time we need for gradient elution is not that much longer as compared to isocratic elution. The question, shall I use carbonate-based or hydroxide eluents in anion exchange chromatography, can very easily be answered. If the application does not require a concentration gradient, carbonate-based eluents are by far the better choice. They are much more inexpensive and very easy to perform. But if the application requires gradient elution, there is no alternative to a hydroxide eluent. In the slide we see the application of both techniques to an unprocessed water sample. On the bottom we see the typical isocratic chromatogram with the carbonate-based eluents. All peaks are separated, we have much more resolution than we even need, but when we compare to gradient elution on the upper chromatogram, we see that fluoride is much better resolved from the system void, as well as late eluting peaks like sulfate and orthophosphate are much sharper, and especially for phosphate we get a much higher sensitivity. Let us switch now to the basics of cation exchange chromatography. In analogy to anion exchange, this slide shows the schematic of the cation exchange process. Again, let us assume that we have a polymeric support particle to which the ion exchange functional groups are attached in one way or the other. In the early days of ion chromatography, the cation exchange functional groups were almost exclusively sulfonate groups. Let us further assume that we have sodium ions in solution, so due to the higher affinity to sodium ions to the stationary phase, those sodium ions will be shortly bound to the sulfonate groups, releasing hydronium ions, so that again we can formulate the equilibrium on the bottom with the selectivity coefficient K describing such equilibrium. And again, if we want to push the equilibrium to the left side, we have to increase the hydronium ion concentration, and in this way we can easily understand that an acid with hydronium ions is a typical mobile phase in cation exchange chromatography. When we discuss the properties of cations that determine retention, we have to discuss the same kind of parameters as in anion exchange chromatography, namely the size, the valency, and the polarizability of cations. However, in cation exchange chromatography there's one more parameter called complexation, and this is always discussed whenever the functional groups of a cation exchanger are not sulfonate groups, but neighboring carboxyl groups. In this particular situation, we would observe complexation of divalent cations. Regarding the valency of a cation, the rule always says the higher the valency of the analyte cation, the larger its retention time. As an example, you see here that the monovalent sodium ion will always be eluted ahead of the divalent magnesium ion, and there's no exception to this particular rule. Regarding size, we always follow the rule: the larger the ionic radius of the analyte cation, the larger its retention time. I've given you here two examples. The first one, the series of alkali cations, and in this case we always see the elution in this order. That means lithium eluting first, followed by sodium, potassium, rubidium, and cesium. Typically, the elution order for alkaline earth metals is exactly the same according to the radius. That means magnesium always elutes first, followed by calcium, strontium, and barium. However, with alkaline earth metals, a reversed elution order between magnesium and calcium is possible and has been described in literature due to complexation. Again, the retention difference between strontium and barium is much larger than the retention difference between the other pairs of cations. This again is due to the large radius of barium ions undergoing non-specific interactions with the stationary phase surface, namely adsorption, and this is the reason why barium is eluting so late. Regarding polarizability, the rule again says the higher the polarizability of the analyte cation, the larger its retention time. The example here in this case is the separation of ammonium and monomethylamine, and we always see that the monovalent ammonium ion elutes ahead of the monovalent monomethylamine ion. The reason for this is that for monomethylamine separation, both ion exchange and adsorption processes are contributing to retention. The classification of stationary phases for cation exchange chromatography is basically the same as for anion exchange chromatography. That means we typically differentiate between different support materials such as silica or organic polymers. In principle, we could use silica-based columns in cation exchange chromatography, as most of the eluents are of an acidic nature. However, polymer-coated silica columns are not that reproducible to manufacture, so that the majority of columns are polymer-based, at least when we want to separate small molecule weight cations. We also differentiate in terms of pore size, and we have heard already that this has an impact on the resulting ion exchange capacity. So microporous columns are usually of low capacity, whereas macroporous cation exchangers are typically of high capacity. There's one little difference in cation exchange chromatography as compared to anion exchange. We still see the use of strong and weak acid cation exchangers. Strong acid cation exchangers with sulfonate functional groups are typically used when we want to have a very high resolution between monovalent cations only, whereas weak acid cation exchangers based on carboxyl or phosphonate groups are typically used whenever we want a simultaneous analysis of mono and divalent cations. This slide shows the development in the design of cation exchangers. A major breakthrough in the development was the discovery of Professor Schomburg in 1987, who was the first to coat silica columns with a polymer called polybutadiene maleic acid. In other words, as you see from the structural formula, we have two neighboring carboxyl groups, and therefore he was the first to simultaneously analyze mono and divalent inorganic cations on such a column material. The idea was great, the implementation was not so great. As I just pointed out, the manufacturing of polymer-coated silica is not that reproducible. Today, we are using organic polymers and grafting polymer chains to the surface, which contain or carry the ion exchange functional groups. And as you can see from the right side of this slide, we are today using carboxyl and phosphonate groups because both phosphonate and carboxyl groups are impacting the complexation behavior of divalent cations. With the right ratio between phosphonate and carboxyl groups on the surface of the stationary phase, we can tailor cation exchanges today so that manganese ions are eluting right in the center between magnesium and calcium ions. As I pointed out earlier, the chromatographic results describe in much easier way the difference between all these design protocols. In the center of the slide, we see a typical separation of all alkali and alkaline earth metals, which are separated here under isocratic conditions with a methane sulfonic acid eluene in less than 30 minutes. I would like to draw your attention to peak number 3, which represents ammonium. Ammonium, as well as other aliphatic or aromatic amines, can all be separated by cation exchange chromatography, but they cannot be analyzed by atomic spectrometry. So this is one of the advantages of cation exchange chromatography over spectrometry. On the lower left, you see a typical example for gradient dilution of cations. In this particular case, we are separating the most abundant biogenic amines, such as putrescine, cadaverine, acmatine, and others. And as you see, due to the higher polarizability, they all are eluting much later as compared to inorganic alkali or alkaline earth metals. Using gradient approach, the entire analysis is done in less than 10 minutes, but of course we have to add the time for the re-equilibration of the column. For the elution of cations from a cation exchange column, we always need an acid eluent. This slide is summarizing the most important acids used in modern cation exchange chromatography. As you can see, we are differentiating between two different groups of acids, the inorganic ones on the top, such as hydrochloric, sulfuric, or even nitric acid, and organic acids such as methane sulfonic or pyridine 2,6 dicarboxylic acid, which is also called dipicolinic acid. The choice of this acid very much depends on the applied detection system. Imagine we would like to separate an aromatic amine, where UV detection would probably be the best choice of a detection system. In this particular case, I would choose an acid with a very low UV background. And whenever I look to this inorganic acid group, of course, I would naturally choose sulfuric acid with a zero background in UV. Imagine I want to use suppressed conductivity with an electrolytically operated suppressor. In this case, I need an eluent which is not electroactive, and therefore we are typically using methane sulfonic acid in this approach. Dipicolinic acid or other chelating agents would always be used whenever I would like to chelate divalent metals. Methane sulfonic acid eluents can also be generated electrolytically. Although I don't have any impurity problems, the electrolytic generation of these eluents is always leading to much more consistent results, especially when applying concentration gradients. The schematic setup is shown on this slide. Everything is exactly the same as we have seen before for the hydroxide cartridge. The only difference is we have methane sulfonate electrolytes in the reservoir connected to anion exchange membranes, and we have the anode in the electrolysis chamber and the other electrode in the electrolyte reservoir. The same thing happens if I'm pumping ultra-pure deionized water into the electrolysis chamber and I apply the electric field between the two electrodes. These MSA minus ions are migrating through the anion exchange membranes into the electrolysis chamber, where these ions are picking up hydronium ions generated at the anode. So my final product is high pure methane sulfonic acid due to the use of a continuously regenerated cation trap column. Also, we see the formation of a little bit of gas. In this case, it's oxygen, which is removed using a high pressure degas unit in a really analogous way. We have the same two scenarios regarding the applied current. It can be held constant for isocratic operation, or it can be programmed over time whenever I want to apply a concentration gradient based on methane sulfonic acid. The second part of this presentation is devoted to detection methods used in ion chromatography. Let me first classify the most important detection method used in ion chromatography today. As you see from this slide, we are differentiating between two different groups of detection methods: the electrochemical methods, usually conductivity or amperometry, and the second group of spectrometric methods comprising of UV-Vis detection, fluorescence detection, or the hyphenation of ion chromatography with element-specific detection in form of ICP, or straight with electrospray ionization mass spectrometry. We already heard that conductivity detection is the most important detection system in ion chromatography. We also heard that for the separation of ions from an ion exchanger, we need an electrolyte in the mobile phase. If we would position the conductivity detector cell directly behind the column, we would face a fundamental problem of having a very large background conductance due to the large concentrations of ions in the mobile phase. This would also mean that we have a large noise level, and noise affects the signal-to-noise ratio and thus sensitivity. In other words, in this so-called non-suppressed approach, we would face a very limited dynamic range of this detection method and a relatively low sensitivity due to the high noise caused by the high background conductance. We should also not forget that the conductivity detector itself, per se, is non-specific. Why? Because it cannot differentiate where the conductivity is coming from the analyte species or from the mobile phase. It cannot differentiate between anions and cations. And we all know and have learned at university, we should not use non-specific detection in general unless we have no alternative. Therefore, Hamer-Small, even in the early days of ion chromatography, has developed a so-called suppressor device, which is nothing else but another ion exchange device positioned between the column and the detector cell. Those suppressor devices are either continuously or periodically regenerated and convert the mobile phase into a less conductive form, and at the same time enhance analyte conductivity by converting them into the corresponding acids or hydroxides. Those suppressors are extremely important whenever we use conductivity detection, but today also for mass spec detection, where I have the same problem. The electrolytes used for the separation cannot be directed straight into the ion source of a mass spectrometer. Therefore, suppressors today are also of utmost importance whenever I hyphenate chromatography with mass spec detection. This slide one more time summarizes the purpose of using suppressors in ion chromatography. I have already outlined the reduction of background conductance caused by the eluent resulting in lower baseline noise. I have already summarized the conversion of the analyte ions into a more strongly conductive form, as well as the sensitivity improvement, the dynamic range improvement, as well as the necessity for suppressors whenever hyphenating ion chromatography with mass spectrometry. However, there are two more reasons highlighted here in red. Whenever I'm using high capacity separator columns in anion or in cation exchange chromatography, we must have a suppressor system in the system. Also, whenever we want to use a concentration gradient in combination with conductivity detection, a suppressor is mandatory. The background of this discussion are the equivalent conductances of selected anions and cations summarized in this table here in this particular slide. As we can see in the first line, the hydroxide and the hydronium ions are having much higher equivalent conductances in comparison with other anions or cations. So if we convert the analyte into the corresponding acid or the corresponding hydroxide, we are not only increasing the specificity of the system, but also the sensitivity. There are numerous suppressor types available on the market today, and therefore it makes sense to differentiate and classify those suppressor systems. We differentiate between batch suppressors, which are typically called packed bed suppressors, and those are available for multiple injections or for a single injection. As we can see from this table, these suppressor types can be regenerated in two different ways, either chemically or electrolytically. On the other hand, we are differentiating between continuously regenerated suppressors, and they can be as well packed bed suppressor types or membrane-based systems, either hollow fiber membranes or flat membranes. Both of these suppressor types can also be regenerated chemically or electrolytically. This slide summarizes the advantages of continuously regenerated suppressor systems. In general, we observe an improved system stability, very low baseline drift and noise, and especially membrane-based suppressor systems are exhibiting a very high suppression capacity, which is especially needed when running concentration gradients. Typically, we don't need any external regenerants such as acids or bases. They are relatively easy to use. There's no additional programming in the software. In conclusion, we have a simplified hardware, no additional valves, allowing a very flexible method development, and overall, those kind of systems are exhibiting an improved reliability. The most common continuously regenerated suppressor systems today are membrane-based systems, and that has a number of reasons. First of all, membrane-based systems have a very small internal volume, for example, only 45 microliter in combination with a standard bore column of 4 mm internal diameter. They are also characterized by a very high suppression capacity, which I already mentioned. As you see from this slide, we can regenerate those suppressors in two different ways. On the left side, chemically, by having a continuous flow of a chemical regenerant through the system. And this chemical regenerant has to be either an acid or a base, depending whether we want to use a suppressor in anion or cation exchange chromatography. The advantage of chemical suppression is that we get the lowest possible noise of typically less than 0.2 nanometers per centimeter. Those suppressor devices are solvent compatible, they are temperature stable, and therefore can be used for almost all kinds of application. The only problem, we need a chemical regenerant. On the other side, you see the possibility of electrolytically regenerating this suppressor device, and we do this by redirecting the water coming out of the conductivity cell into the regenerant chamber of the suppressor. If we again apply an electric field between two different electrodes, we can split these water molecules into hydronium and hydroxide ions, which we need for the regeneration process. The advantage of this setup is simply ease of use. Whenever you're switching on this system, everything works. If you switch it off in the evening, everything stops. Very easy to use, but the lifetime of such a device is smaller than the lifetime of chemically regenerated suppressors. We have heard about the various types of suppressors and their impact on conductivity and mass spec detection. Let us now have a look into the inside of such a suppressor and how it works. As an example, this slide shows the schematic of an anion self-regenerating suppressor. In the center of the slide, we see the eluent chamber with a two cation exchange membrane on each side. On the other side of the membranes, we have the regenerant chambers and the two electrodes. We also see that the flow of water through the regenerant chambers is countercurrent to the flow of eluent or analyte ions in the eluent chamber. If I'm now applying an electric field between the two electrodes, we see the formation of hydronium ions at the anode, and those hydronium ions, under the influence of the electric field, are migrating through the cation exchange membrane into the eluent chamber. Likewise, all the cations in my mobile phase or the cations of my analyte species are also migrating through the cation exchange membrane towards the cathode. In this way, I get the conversion of potassium hydroxide eluents into water and the conversion of the analyte species into the corresponding acid. For the analysis of ions with pK values above 7, suppressed conductivity does not work because the corresponding acids or bases are simply not dissociated. In this situation, we very often use amperometric detection. The cell of an amperometric detector consists of three different electrodes: the working electrode, the reference electrode, and the counter electrode. Working electrode materials can either be precious metal such as gold, silver, or platinum, or various forms of carbon like glassified carbon or carbon paste. Reference electrodes are typically a silver-silver chloride one, or a pH electrode, or combination of both. But lately we also see the use of palladium hydride electrodes, which have the advantage of a much longer lifetime. The counter electrode is either glassified carbon or simply the stainless steel body of the electrochemical cell. The working principle: we either observe an oxidation or reduction of an electroactive compound, and therefore we are generating either an anodic or cathodic current being proportional to the analyte concentration in a certain concentration range. Oxidation reactions are much more common than reduction reactions. In this slide we see a table with working electrodes and oxidation potentials for selected inorganic electroactive compounds. Sulfide and cyanide, as examples for toxic ions, are usually oxidized on a silver working electrode, as well as halides such as bromide and iodide, or pseudohalides like thiocyanate or thiosulfate. Sulfite, hypochlorite, arsenide, and hydrazine are typically oxidized on platinum working electrodes, while nitrite, chlorite, and thiosulfate can also be oxidized on carbon paste electrodes. The next slide summarizes some of the basics of amperometry. Let us assume the amperometric detection of a compound A being oxidized to compound B and releasing a number of electrons. These electrons are forming a current, and this current is what we actually measure in amperometric detection. The whole process is described by the very famous Nernst equation, describing the relation between the concentration of the oxidized and reduced species and the applied potential. In the formula below, we see the standard potential E0, and this is the potential at which the concentration of A and B are equal. Single potential, or direct current amperometry as it is often called, is the most widely used method of electrochemical detection in liquid chromatography. Single potential amperometry means that we apply the oxidation potential at all time and that we measure the resulting oxidation current at all time. The applied potential can be adjusted to maximize the response for the analyte of interest while minimizing the response for interfering analytes. We generally observe that with increasing oxidation potential, more and more electroactive species can be oxidized, but we also see more and more interferences. In other words, the lower the oxidation potential, the higher the specificity of the method. Are several ions with different standard potentials to be analyzed in the same run, we have to choose a working potential that covers the diffusion-controlled plateaus of all analyte ions. A very important example of DC amperometry of inorganic anions is the analysis of sulfide and cyanide. As you can see from this slide, both anions are separated very well on a Dionix carbopacked Pa1 column with a high concentration of sodium hydroxide and sodium acetate in the eluent. The mobile phase also contains a small amount of ethylene diamine to chelate ultra traces of transition metals in the mobile phase. The electrochemical oxidation takes place at a silver working electrode when applying an oxidation potential of 0 volts. Imagine we want to analyze cyanide in a real-world sample that might also contain traces of transition metals. Without any sample preparation, I would encounter some severe problems because we all know that cyanide is chelating transition metals to form hexacyano complexes. In other words, without any sample preparation, I could not differentiate between the toxic free cyanide in the sample and the complex cyanide which might release free cyanide during the chromatographic process. Therefore, the sample preparation which has to be used is an acid distillation of cyanide into an alkaline absorber. This alkaline absorber is typically a 1 molar sodium hydroxide solution, and now we understand why we use a high concentration of sodium hydroxide as the eluent, so that we don't see any interference from the alkaline absorber as the matrix. If I do this kind of sample preparation, all matrix effects are removed, and that explains why those chromatograms of sulfide and cyanide always look very clean. The big advantage of electrochemical detection of sulfide and cyanide is a very high sensitivity. We can analyze these two ions down to single-digit part per billion levels with this methodology. Another variant of amperometry is pulse amperometry. The driving force for its development was a search for detection methods for carbohydrates. It was known for a long time that carbohydrates are electroactive. However, if I'm applying DC amperometry, the oxidation products are fouling the electrode. Based on the pioneering work of Professor Dennis Johnson, who at that time worked at the Iowa State University in the United States, pulse amperometry was introduced in 1983. In pulse amperometry, the working potential is applied only for a very short time, usually a few hundred milliseconds, followed by a series of lower and higher potentials that are used for cleaning the electrode electrochemically. The current, however, is measured only while the working potential is applied. Immediately after the pulse in the diffusion controlled plateau area, the measured current is very high because the molecules A in the vicinity of the electrodes are immediately oxidized. More distant molecules are transported to the electrode surface by diffusion and are then oxidized so that the current decreases accordingly. During the oxidation of A to B, two different currents are generated. The charging current, first of all, charging the layer between the electrode and the solution, acting as a capacitor, and the so-called Faraday current, which describes the electron transfer during the oxidation from A to B. The next slide shows the four potential waveform for carbohydrate detection as it is used today. As we can see from the slide, the oxidation potential for carbohydrate is 0.1 volts, but you can also see that we are waiting a little bit of time before we start data acquisition. This so-called delay time is necessary because I just mentioned that we are generating two different kinds of currents, the charging and the Faraday current. The good thing is that the charging current decays much more rapidly than the Faraday current, so if I'm waiting a little bit of time, I can truly measure the Faraday current only. After about 200 milliseconds, I start doing data acquisition, and as you can see, we are not measuring the current itself, we are integrating the signal over this period of time so that we are in fact measuring charge, usually in nanocoulombs. After data acquisition is finished, we are cleaning the electrode with a strongly negative potential and then apply a positive potential of plus 0.6 volts, and this is due to the formation of gold oxide, which is necessary for the carbohydrate oxidation. After a very short time, we reduce the gold oxide back to gold plus minus 0, and after this electrode activation is done, we can go back to the original starting conditions of 0.1 volts and start the next pulse sequence. Applying this waveform, we can measure carbohydrates at a very sensitive scale. Today, we are detecting mono and disaccharides down to the femtomole level. With the application of such a four potential waveform, we also get a very stable signal over a long period of time. A typical example of the pulse amperometric detection of carbohydrates is shown on this slide with the analysis of inulin. Pulse amperometry does not work at pH values below 11. What looks like a disadvantage is actually very beneficial if we want to employ anion exchange chromatography for the separation of carbohydrates. It is known that carbohydrates are molecular compounds at neutral pH, but it is also known that carbohydrates are very weak acids with pK values above 12. So if I'm using a mobile phase with a pH level above 11, I'm converting carbohydrates into anions and thus can use anion exchange chromatography for the separation. In this slide, we see the chain length distribution of inulin, which is a polyfructane with lots of fructose units coupled together. Such a separation cannot be done with a pure hydroxide mobile phase. While fructose itself can be separated with pure hydroxide, higher oligomers of fructose cannot. They would be retained on the column for a very long time. Therefore, I'm using a sodium hydroxide eluent with a concentration of 0.1 mole per liter to just maintain pH 13 and overlay this with a concentration gradient of sodium acetate. Sodium acetate, in fact, acts as a pushing ion, and it can be added at very high concentration because it's not electroactive. That means it has no negative impact on detection. What we also see is that we have a very shallow gradient approach in this case to get the superior resolution which you see in this slide. The little hump at the end of the chromatogram is due to high molecular weight compounds in this particular sample. The third variant of amperometry is integrated pulse amperometry. This technique is applicable for the analysis of amino acids, for amines in general, and for divalent organic sulfur components. The biggest difference in comparison with pulse amperometry is that the oxidation potential E1 is varied in a cycle between a high and a low value during data acquisition. Professor Lacourse, working at the University of Baltimore in Maryland in the United States, discovered this effect at the end of the 1990s. Analyte and metal oxidation take place at the same time at the higher potential. However, the metal oxide formed at that potential is immediately reduced at the lower potential. So since the oxidation of the electrode surface is reversible and the oxidation of the analyte is not, the resulting signal is characterized predominantly by the contribution of the analyte oxidation. By integrating the current yield during this cycle, the net signal for the respective analyte is resulting. As an example for integrated pulse amperometry, we see in this slide the waveform for amino acid analysis as it is used today. As you can see, the waveform now consists of 6 different potentials, and believe me, every one has a meaning. However, I want to repeat the most important fact is that we are cycling the oxidation potential between a lower and a higher level during the integration period. Cleaning the electrode and activating it afterwards is exactly the same as in the 4-potential waveform developed for carbohydrates. Applying this 6-potential waveform, we can detect amino acids directly down to the picomole level. Integrated pulse amperometry has somewhat revolutionized amino acid analysis. In the past, we either had to use pre-column or post-column derivatization in combination with either reversed phase or cation exchange chromatography, respectively. The separation in this slide shows proteinaceous amino acids. That means the one which we see when hydrolyzing a protein. However, peak number 2, ornithine, is a physiological amino acid but can also be analyzed in the same run because it is an acid. We know that under the term physiological amino acids, we are summarizing up to 44 different components, some of them being amines which are not retained on an anion exchanger. Like with carbohydrates, we are separating amino acids on an anion exchanger at high pH, which also favors the subsequent electrochemical detection. The eluent is very similar, consisting of sodium hydroxide to maintain a high pH and a sodium acetate gradient. The separation is usually started with a pure hydroxide eluent to get the resolution in the front part of the chromatogram, and then we overlay a sodium acetate concentration gradient because aromatic amino acids are very strongly retained and cannot be eluted with pure sodium hydroxide. When we compare anion exchange separations with those on cation exchange columns, the only difference is the elution order. Arginine eluting first on an anion exchanger, as an example, elutes last on a cation exchanger. The time for both separations, anion or cation exchange, is very much the same. With the next slide, let us quickly review UV detection for ion chromatography. In ion chromatography, UV detection is not as significant as it is for conventional reversed phase chromatography. The reason for that is very simple. Most of the inorganic anions and cations do not have any chromophores. However, when analyzing strongly contaminated samples, many people are using UV detection in combination with suppressed conductivity detection. The next slide shows a table with the UV absorption wavelengths for selected inorganic anions. We see that metal chloro or metal cyanic complexes, nitrite, nitrate, some sulfur components like sulfide, thiocyanate, and thiosulfate all absorb in a wavelength range between 200 and 250 nanometers. There are two exceptions. Chromate absorbs at 365 nanometers and iodide at 227. I just mentioned that UV detection very often is used in combination with suppressed conductivity detection. This slide shows a perfect example, the analysis of inorganic anions in a strongly contaminated water sample utilizing both detection systems. The sample in this case is a synthetic wastewater with 2 grams per liter sodium chloride. Let's have a look to the top chromatogram representing suppressed conductivity detection. We see that later eluting peaks such as bromide, nitrate, orthophosphate and sulfate can easily be separated and quantitated under those conditions. However, the small nitrite peak is on the tail of the huge chloride peak and therefore cannot be quantitated under those conditions. We also see a signal eluting slightly earlier than fluoride. And this is due to the high chloride content of the sample, which overloads even this high capacity anion exchanger, and therefore such a signal can easily be interpreted as a displacement signal. Eluent in this case is displaced by the large chloride concentration when it hits the column. The bottom chromatogram represents UV detection, and we can easily see that the 3 UV absorbing ions, nitrite, bromide, and nitrate, can easily be quantitated under these conditions. We also see one strongly negative peak and later on 2 smaller negative peaks appearing in the chromatogram. Now the eluent here in this case is 9 millimole per liter sodium carbonate that has a slight UV background. That means whenever larger concentration of UV transparent ions are passing the UV detector cell, they lower for a short moment the background absorbance and appear as negative signals in the chromatogram. Towards the end of my presentation, let me make a few comments regarding the applicability of ion chromatography. In my introduction, I have already mentioned that the perception of ion chromatography 40 years ago was completely different from what it is today. At that time, people believed that ion chromatography can only analyze inorganic anions and cations. Today we know that this situation has changed dramatically. This slide gives you just a few examples of anionic species here shown on the left side of this slide. On the top, the huge area of organic acid analysis, amino acid analysis, polyvalent anions being components of a lot of consumer products today, the huge area of polarizable ions with large radii, anionic surfactants, and in the life science area, the separation of carbohydrates, proteins, and oligonucleotides. We should not forget that up to the present day, the highest resolution separations of carbohydrates and proteins are done by ion exchange chromatography. On the right side of this slide, you see a few examples for cationic species. On the top, the very important class of amines. Transition metals are usually only analyzed by ion chromatography if the oxidation state of the metal is of interest. On the other hand, lanthanides are almost exclusively analyzed by gradient ion exchange chromatography. Phosphonium, sulfonium, hydrozinium compounds are certainly not that common, but a very important class of cationic species are cationic surfactants, also used in many consumer products today. All in all, one more time, we can separate today, without any exaggeration, almost any ionic or ionizable compound with any one of the techniques summarized under the term ion chromatography. In conclusion, over the past more than 40 years, since its introduction in 1975, ion chromatography developed to be the most dominant method in ion analysis today. This is due to many reasons. One of them is the speed of analysis which we can achieve today, obtaining complete anion or cation profiles in less than 10 minutes, using capillary ion chromatography today even in less than 5 minutes. We have a large variety of stationary phases in combination with many specific detection methods, and that makes, as I just pointed out, a C applicable to almost any ionic species. Determinations down to the sub-microgram per liter level without pre-concentration demonstrate the high sensitivity of ion chromatography today. At the end of this presentation, let me acknowledge one more time Hamish Small. I think we all agree without him, we probably wouldn't have ion chromatography in the form we have it today. I also would like to acknowledge Chris Paul and his entire R&D team in Sunnyvale, California. Without his work and the work of his co-workers, we would not have all these fantastic stationary phases which we can use today. Professor Sandy Dasgupta and Paul Haddad, two professors that made numerous contributions to the field of ion chromatography. Dennis Johnson and Professor Bill Acorce, two professors that are very closely related to electrochemical detection in ion chromatography. Phil Jones and Pavel Nestorenko, very closely related to the big subject of chelation ion chromatography. And you will believe me, there are many others who contributed to this field of science in the past or up to the present day. With that being said, thank you all very much for your kind attention, for your interest in this subject. If you have any specific questions, please feel free to contact me at any time. I have given you my current email address on this slide. Thank you so much again.